Okay, so good morning or good afternoon, depending on where you are. Today I would like to talk about Comet 1P Halley and its associated meteor showers. So 1P Halley is a very famous comet that moves on a retrograde orbit with a period of 70 to 80 years. And since a comet often appears very bright in our sky, the first observations of Halley date to more than 2,000 years. And that's why we're able to trace back the motion of the comet during 3 millennia with a good accuracy. Halley is known to produce 2 meteor showers on Earth, the Orionids around the ascending node in late October, and the Eta-Aquariids around the descending node in early May. And these showers are called the Halley's. And you can see that the current nodes of Halley's orbit are located at very different distances from Earth's orbit. But despite of that, the Halley's share similar characteristics. They have more or less the same duration, also about the same average activity level of 40 and 70 meters per hour. And they both display several peaks of activity that are variable in time and intensity. And so these characteristics cannot be explained by a simple toroidal model of the meteorite stream, but they were qualitatively explained by the shell or the ribbon-like model proposed by McIntosh, Hajduk, and Jones. And to understand the shell model, it's actually quite helpful to visualize the past motion of the comet. So in this animation, you see how Halley's orbit, represented in purple, changes with time. And because of the comet precession, you see that the node's location here in green and orange also change rapidly. And the idea behind the shell model is that meteorites ejected by the comet will precess at different rates, some staying on orbits where the comet was a long time ago, and other ones following the comet evolution or even reaching Halley's future positions. So these meteorites will form this kind of ribbon-like structures that will produce similar meteor showers on Earth. We also know that the Halley's display occasional outbursts reaching 2 to 4 times their usual activity level. This occurred, for example, in 2006 and 2007 for the Orionids, and 2004, 2013 for the Eta-Aquariids. And it has been shown that most of the major Halley outbursts are actually caused by meteorites trapped into mini-motion resonances with Jupiter, and especially the 1-6 mini-motion resonance. So we see that all these previous works already explain several features of the shower. So why do we need a new model, right? Well, essentially because we lack of quantitative predictions. There is no forecast of the shower's activity in terms of peak time, intensity, or duration. And the situation is even worse for the Eta-Aquariids due to the paucity of published observations until recently. We also see that numerical models of the showers so far haven't reproduced a similar activity level and duration of the Halley's, and that we don't have any strong constraint on the age of the shower. And we've published estimates ranging from 10,000 to 100,000 years. So that's why we decided to develop our own model of Halley's meteorite streams. So to do that, we adopted a very common methodology in meteor showers modeling. First, we reproduce the comet past activity and ephemeris. Then we eject thousands of simulated particles at each apparition of the comet. We integrate them, and we select the meteorites that are assumed to collide with Earth. And after some waiting and processing, we finally obtain our simulated meteor shower. And the core of our approach is really to calibrate and validate our simulations on decades of meteor observations. So for the Halley's, we have simulated more than 5 million particles ejected from the comet since 3,000 years BC. We have integrated them, and then we have carefully calibrated them on 35 years of Eta-Aquariids and Orionids observations. So the first part of this project was really to compile and analyze all these observations in the visual, video, and radio range that were collected by the International Meteor Organization and the Canadian Meteor Orbit Radar. So here in this figure, you just have an example of the activity profiles we used for the Eta-Aquariids calibration. So now I will briefly present the main results we obtained with our model. And in the following plots, the red color will always refer to the simulations and the other colors to the observations. So we see that with our model, actually, we're able to reproduce most of the Eta-Aquariids activity profile, what you see here on top. And the agreement is also good for the Orionids, but we generally miss the end of the shower's activity. And this remains true when we compute the average activity profile. Like here, our simulations reproduce very well the Eta-Aquariids, suggesting that the age of the shower slightly exceeds 5,000 years. But in contrast, our missing part of the activity profile suggests that the Aurianids may be older than that. And even if we slightly underestimate the Aurianid average activity, we have with our model for the first time similar activity levels for the two shower. We have also being able to simulate the mass distribution of a meteor shower for the first time too, to our knowledge. And if our estimates of the mass index actually depends on the calibration and the mass range we consider, we see that in the visual range, we really approach the observed average of 1.87 for the showers. So that's cool. And when we look at the year-to-year variations, you see that our model, so here in red again, reproduces the main peak ZHR since 1995 with an error lower than 30%. So this really increased our confidence in our simulations and impulsed to try to extend this model until 2050 and forecast the activity of the showers. So for the future, we predict 4 Eta-Aquariid outbursts in 2023, 24, 45, and 46. You have some examples of the predicted activity profiles here in this plot. And especially in 2024, we find that most of the activity, the peak, is caused by a trail that was ejected when the comet was trapped into the 1-6 resonance with Jupiter. So we might have another example of an Halley's outburst caused by the 1-6 resonance. So it will be super helpful to observe the activity of the shower in the coming years, and especially in 2024, to confirm this prediction and refine our model. For the Aurianids, we expect no significant outbursts until 2050. Our simulated rates, this time in black, oscillate between 10 and 40 meters per hour. And actually, this is what has been observed in the past for the shower. And because of these oscillations, several authors suspected the existence of a close to 12-year cycle in Aurianian activity. But this is really hard to confirm only with the observations, because you see that continuous observations of the shower cover maybe 2 cycles of 12 years, and only 1 if we take into account other detection methods like radio or video. So to be sure of this periodicity, we need to observe the Aurianids activity during at least another 12-year cycle. Or we can also investigate that with our model that covers a period of 65 years. So here in red again, you have like our simulated ZHR rates for the Aurianids. And when we try to fit this red curve with a sinusoidal function, the best match is obtained for a period of 11.83 years, which is very close to Jupiter's orbital period. So we have investigated that a bit deeper, and it seems that our model supports the existence of a close to 12-year cycle in Orion's activity that is again induced by the 1-6 mid-motion resonance with Jupiter.
2 minutes.
Okay. Oh, well, I was fast. So to conclude, I will say that we have developed the most complete model of the Halley's meteorite streams to date. Our simulations reproduce most of the Eta-Aquariid characteristics, and it's also true for the Aurianids, but we generally miss this end of the shower's activity. So this suggests that the age of the Eta-Aquariid somewhat exceeds 5,000 years, while a greater fraction of the Aurianids is composed of older material. Since we are able to reproduce the general characteristics of the shower, you see in this plot an example, our simulations even reproduce this ribbon-like structure that was predicted by McIntosh and Hajduk. So we extended this model until 2050 to forecast the shower's activity. And it highlighted once again the influence of the 1-6 mid-motion resonance with Jupiter on the stream's evolution. This resonance is known to cause several Halley's outbursts, but also maybe to induce this 12-year cycle in Aurianid activity. And for the future, we predict 4 Eta-Aquariid outbursts, the 2 closest one being in 2023 and 2024. So it will be great if we just can monitor these showers in the future. And in a more general way, I think this work really is a nice illustration of the progresses we're making in combining lots of meteor observations with numerical simulations of meteorite streams. If the model is like complete like that, it's really because we had years and years of meteor observations in several magnitude ranges. So I really hope we're gonna continue observing and modeling together for a long time. Thank you very much.
Thank you. Again, a perfect timing. Now is end. The end is near. Thank you very much. Can you please remind me
Yes.
when is actually Halley turning back? Is it in 4 years' time or something like that? Right
It's
now.
in 2081 or 71, something like that. Oh,
No.
2061.
When it is turning back on the orbit, now it is still receding, and now it's turning back to approach us again. I think it
I
is
think
in
it's
2024,
no,
25.
it's later than that. It's in 2061, I guess.
No, that's when it is back, but when it
Oh,
is turning back on the orbit, at the farthest point and at
oh,
aphelion.
okay. Oh, yeah. I don't have the data right now. Sorry.
Anyway, it will
Irko.
stay there a long time because it goes very slow there.
Yeah.
Yeah. Anyway, I remember someone proposed to have a celebration of Halley is turning now back to approach us. I know that the next close approach is 2061, but the time when it is
Okay.
starting to approach is in a few years' time. Okay, Circo.
Auriane, about the 2023-24 outburst of the Eta-Aquariids that you predict, what will be the shape of the profile? Will it be that just the overall level will be higher by a factor 1 of 2, or do we have like a narrow peak at some definite time?
Yeah, this is what I guess. So you have like the peak is quite large, but I mean it's at the usual expected time for the Eta-Aquariids, around like 45 degrees in solar longitude, and this is what I have. So generally in the simulations, I slightly underestimate the shower here at higher solar longitudes, but yeah, this is what I have with my simulations, this kind of shape here.
Which means it can probably be observed at every part in the world because it lasts longer than just a few hours or so. It might be like a day or two.
Yeah.
Cool, thanks.
I have a question as well.
Yeah.
Yep.
First, thanks for this great work, to also combining observations and modeling, which I like a lot. And did you try to look back into older archives to follow this 12-year period? I remember that for this resonant case for the Aurianids, I looked back in archives and found just something about 1920 or so, but it's not continuous. Did you try anything like this, looking back?
Yeah, I mean, I try to compare with like ancient observations and the observations in the early 20th century. All the details are like in these two papers here, but actually it was kind of hard because I wasn't really sure of, I mean, the observations were sometimes a bit contradictory. And so it was hard to really use them. For example, we noticed periodicity in the location of the main peak of the Aurianids, but then I was like matching some of these observations and not the other ones. And so it was a bit more confusing. So that's why I really focused this work on actually more the period between 2002 and 2020, because we have like visual observations and radio observations for the showers.
Okay, thanks.